Okay, this is section 3.3, and problems 5 and 6 were asked about, and as was 12. So I'm going to work on those here with you. First of all, we could just graph this, and if we use Desmos, it can help us out pretty well, but it's hard for me to switch from Desmos to this. But we can look at this. Typed it in, and it's going up. It'll reach a max in here, comes back down, reach a minimum, and go back up. A third degree equation will do something like that. So it must be increasing up until the maximum, and then decreasing till the minimum, and then increasing. So we need to know where the max and mins are. So to do that, we need to know we set the first derivative equal to 0. So if I take the derivative of this, that would be 9x squared minus 36, and the derivative of 3 is 0. So if I set 9x squared minus 36 equal to 0 and add 36, I get, and then divide by 9, I got x squared equals 4. Because minus 36, add it, it's 36, divided by 9 is 4. And so x is going to be plus or minus 2 when I take the square root. And so that says on here at minus 2 it must have reached its maximum, and at plus 2 it reached its minimum. Now, I can tell that from graphing. I can also tell, since it's a cubic, that it has to go up, and it's a positive here, goes this matter. So I know it's increasing up until, so the interval it's increasing is from negative infinity up to negative 2. At negative 2, it's changing, so we don't include it, not a square. Union, the other place it's increasing is from 2 to infinity. And where is it decreasing? It's decreasing from negative 2 to 2. Now, we can also check by just, if we didn't have a graph to look at or didn't know this, we can check. We have negative 2 and 2 as our two dividing places. And I could put something lower than negative 2 in here, like negative 10, and see whether this is positive or negative, because this is a slope. A negative 10 would come out to be a positive slope, and it would be increasing. If I put something in between, like 0, I get plus 3, which is, no, excuse me, into this. If I put in negative 10, I get 900 minus 36 positive. So this is going up. Then if I put something in between negative 2 and 2, I get like 0, I get negative 36. It's decreasing. And then if I put something past negative 2, like 3 or 4 or 10, I get positive numbers, and it's increasing. So I can tell whether it's increasing or decreasing without looking at the graph and without anything else. I could just plug in numbers over in this area into the derivative and find out it's got a positive slope. Numbers in here, in for the x's, and I get negative slopes and then positive slopes. So that's the idea there. Now, find the points where it achieves its local maximum. So we know what happens at maximum at negative 2, and I'd have to put negative 2 in there to find the total point. Negative 2, comma, and that would be 8 times 3, negative 24. And negative 2 times that is positive 72 plus 3. So it's positive 75 minus 24 is 51. Local minimum is happening at plus 2. And to get the height, I get positive 24 minus 72 plus 3. So a plus 3 to the minus 72 makes 69. Minus 4 is 65. Minus 20 is 45. Okay, now the concavity changes just once. It's concave down and then it's concaved up. The concavity is when the second derivative, which is 18x plus nothing, because the derivative of that's 0, when that's 0, well, 18x equals 0 when x equals 0. So the intervals where it's concaved up, we could check whether it's concaved up over here. We know it is because we can look at the graph, but put something bigger than 0 where the concavity changes, like put in 2, and 2 times 18 is 30. It's positive, so it's concaved up. So it's concaved up from 0 to infinity, and it's concave down before that, and we could have put in -2 in here and got -36. It's still, I guess, concave down, but from -infinity to 0, it's concave down. And the inflection point, it happens at 0, and if I put 0 in the original one, I get 3. Okay, so this one, I won't even graph. It's a positive and it's x to the 4th. I'm going to sketch. 4th, it could do something like that. And it's positive, so it's going up. So I know it's decreasing, increasing, decreasing, increasing. But I'm going to find the derivative, which would be 12x to the 3rd minus 12x, and the derivative of 9 is 0. Well, they've picked this nicely so that we can, setting this equal to 0, we can factor a 12x out of it and get x squared minus 1. And so this happens when x equals 0, and this will be 0 when x, if I factor that, it's x minus 1 and x plus 1, when x equals 1 or when x equals minus 1. So I know the quartic looks like something like this, so at minus 1 must be a minimum. We can check that in just a sec. At plus 1, it should be a minimum, and at 0, it should be a maximum. So input the intervals where it's increasing, from minus 1 to 0, and from 1 to infinity. Input the intervals where it's decreasing, from -infinity to minus 1, and from 0 to 1. These are all x values. Now, if I wasn't sure that it looked like this, I could pick numbers between them. That's the idea of the sign chart that's talked about. So something before minus 1 would be minus 2. Minus 2 cubed is minus 8 times 12 is minus 96. Minus 2 times 12 is plus 24. This is going to be a negative value. So it has a negative slope over here. So I know it's decreasing. Then I could put something between minus 1 and 0, like a minus a half in here, find out that it's a positive slope, so it must be increasing. And then it must be decreasing. And then it must be increasing by just plugging numbers between these critical values to find out whether it's increasing or decreasing. Now it says find a local maximum. Well, there's only one, and it happens at 0. And if I put 0 into this equation, I get 9. Find the local minimum. Well, there's 1 there at -1. I'd have to put -1 into this equation. And -1 to the fourth is 1 times 3. 3 -1 squared is 1 times -6 is -6 plus 9. So putting -1 in, I get 3 minus 6 plus 9. That is 12 minus 6, 6. So this is at -1 plus 6. This is at 0, 9. And this one's got to be down again. And let's find out what that is. And that's at 1. 1 in here is 3. 1 in there is -6 and -9. So it's also at 6. High. Find the intervals when it's concave down. Well, it's concave down here. And, no, that was another minimum up here. 1, 6. Concaved up, that would be from here to there and from here to there. So I have to find these inflection points is where it changes from concave up to concave down. We find those by setting the first derivative, in other words, the second derivative, equal to 0. So that would be 36x squared minus 12. That's the derivative of this. I set that equal to 0. So that would be minus 12 equals 0. So I'm going to add 12 to the other side. And then I'm going to divide by 36, and I get x squared equals, 12 over 36 is 1/3. So the inflection points happen at plus or minus 1 over the square root of 3, if I take, or square root of 1/3. So this one is minus 1 over the square root of 3 in the x, and I'd have to put it into this to find the y value. And this one's at plus 1 over the square root of 3 something. So the interval where it's concaved up is from -infinity up to there. -infinity up to minus 1 over the square root of 3. And it's also concaved up from 1 over the square root of 3 to infinity. And it's concave down between those two. Minus 1 over the square root of 3 to 1 over the square root of 3. And the inflection points are minus 1 over the square root of 3 plugged into here. Let's see. Is that difficult? 1 over the square root of 3 minus, it's going to be this, since these even powers, it's not going to make a difference. They're going to be the same height. 1 over the square root of 3 squared is 1/3. To the fourth would be 1/9 times 3, so that's 1/3 plus, this is going to be 1/3 times 6, which is -2, and this is going to be plus 9. So it's 9 minus 2 is 7 plus 1/3, 7 and 1/3. And when I put positive the other one in, 1 over the square root of 3 to the fourth, it's going to be the same thing. So the other one, inflection point, is at 1 over the square root of 3, 7 and 1/3. Okay, 12. Suppose that g of x is a function that's continuous everywhere every value of x not equal to 2. And the first derivative looks like this. And that's obviously not going to be continuous at 2 because you can't divide by 0. Further assume that it is known that g is a vertical asymptote at 2. Well, we know that already. We can look at that and see that. In fact, from pre-calculus, you should know that this has a vertical asymptote at plus 2. It crosses x at minus 4. And it bounces at plus 1. So it bounces off of either the top or bottom. We don't know whether it bounces this way, because that's a double factor. And so it could come this way, bounce and go up, or it could come down and bounce and go down. And since this is a single factor, if it goes down, it has to come from above. And if it goes up, then it has to be down here. So to find out, I'm going to find out what the y-intercept is. So I'm going to put 0 in for all the x's. And if I put in 0, I get 4 times 1 over minus 2. So it crosses at negative 2. So if it goes through there and it bounces here, it must do something and crosses over here, must do something like that and then like this. Did I get the y-intercept right? Let's make sure. Put in 0, I get 4. Put in 0, I get minus 1 squared, which is 1, so I get 4. Put in 0, I get minus 2, so it crosses at minus 2. X is 0, minus 2. Okay, so it looks like this is concave down, then concaved up, then concave down, then concaved up. Looks like there might be a maximum over here and as this flattens out. Because, oh no, this will have a sloping asymptote. It's going to be either following a line like that or a line. This is going to have, it's going to follow a parabola. And this is going to go up like this somehow. Because the degree of this is 3 and this is 1, so 3 minus 1 is 2. This will be a shape of a parabola. But determine the critical numbers of G. So we need, oh, my. Forget everything I just said. I thought this was G. This is the derivative. The derivative looks like this. So the critical numbers are when this is 0, which is at minus 4, and at 1 makes that be 0, and that's it. Those are the two critical numbers. By developing carefully a labeled first derivative chart, decide whether G has a local maximum and local minimum or neither. So this is where we do the sign chart. So not this function, but we need to know what G is doing. So we need to know the slope. There's 3 places we've got to be concerned about. Negative 4, 1, and 2. So I'm going to break up my graph in from below negative 4, between negative 4 and 1, and between 1 and 2, and beyond 2. So now we have to find out whether the slope is positive or negative. So we're going to put something below negative 4, like negative 5. This squared is always positive. If I put negative 5 in here, that's negative. So negative times the positive is negative. If I put negative 5 in here, negative 5 minus 2 is negative. So I got a negative divided by negative, which is positive. So my graph has a positive slope before negative 4. Not this graph, the graph I'm trying to graph. It has a slope of 0 at negative 4, but it has a positive slope before then. I don't know whether it's above or below the axis, but it's growing till then. Then it has, it's probably a max. We'll check in here. Between 1 and minus 4, 0 is an easy number. This would be positive, this would be positive, and 0, that would be negative, so it's negative. So it's plus here, minus in here, so it's decreasing, according to my sign chart. Then I got to look between 1 and 2, like 1.5. This would be positive, this would be positive, and 1.5, this would still be negative, so it's still decreasing after 1. So I'm guessing it does something like that. And then we got to go after 2, like 3. That would be positive, that would be positive, that would be positive. Everything's positive. So then it's going up after that. Okay. So decide whether it has a local maximum. I think there's a local maximum at negative 4. I don't think there's a local minimum, and or neither at each critical. At this critical, it's neither. At this asymptote, it's neither. And at minus 4, it looks like there's a max. Does G have a global maximum? Well, I think it looks like it has a positive slope, so it may go on forever, may not, or might be there. It may not get higher than 4. Does it have a global minimum? Because of this asymptote, it doesn't look like it. It looks like it keeps going down forever. So I would say no here, and I would justify by, well, I can't graph this because I don't know the antiderivative of that. So I'm going to guess it has a local max. Don't know what happens here. It's got a positive slope. And if it stays positive all the rest of the way, I suppose it has to go higher. So I would say no global max. It keeps going up and up and up. What happens to the derivative as x gets really large? So I'm looking at this. As x gets larger, what's the slope do? Does it get steeper or not? Well, this will keep growing, this will keep growing, and this will grow, but this will grow less than those. So it's going to, do you know what I mean by that? An x to the third, if that was multiplied out, grows faster than a line. And so it's going to keep going to infinity. And so what does that limit tell us about the long-term behavior? That the slope gets more and more positive, so it goes off to positive infinity. So I've already kind of scheduled a possible graph for this. Goes off to infinity. Okay?